This sample problem involves the concepts of friction, force, work, and we'll bring in the kinematic equations as well. But our situation is we have Sean dragging a bag full of mulch, so mulch is in plastic, dragging across the grass. The surface is horizontal. We'll assume that unless we're told otherwise in problems. The mass of the bag is 45 kilograms. And Sean's pulling here with 135 newtons of force, but not pulling horizontally, pulling partly horizontally and partly upward. The angle of Sean's force is 25 degrees up from the horizontal. There's a coefficient of static friction between the bag and the grass of 0.3 and a coefficient of kinetic friction of 0.25. As is usually the case, the coefficient of kinetic friction is smaller than the coefficient of static friction. We want to do three types of calculations. We want the work done by Sean on the bag of mulch. We want the work done by friction on the bag of mulch. And they're going to have 3 meters of motion involved here where we want this work to be calculated. And then lastly, we want to know the final velocity of the bag, its speed along the ground after it's covered the 3 meters of distance, and we're going to calculate this in 2 different ways. I'm going to calculate that speed in 2 different ways. So you should read through a problem a couple of times and then make your own quick little sketch. So in this sketch I've got this blue rectangle, that's the bag of mulch, and showing forces that are acting here. The force of kinetic friction to move 3 meters, we have to have kinetic friction, not static friction. I'll talk about why we're using kinetic friction and why the bag moves at all. And then we have Sean's force, 135 newtons, angled up from the horizontal at 25 degrees. And we're going to be displacing the bag off to the right in this diagram. It'll turn out, as I've worked ahead, I know the answer here. It turns out that Sean's force is greater than the force of friction, greater than the force of static friction, and greater than the force of kinetic friction. And when I'm talking about Sean's force, I should clarify that. Sean's force in the horizontal direction, off to the right, a component of the 135 newtons, and we'll calculate that, is greater than either the force of static friction or kinetic friction. Well, to calculate work, we need to take force times displacement. But that simple statement has a requirement. The force and the displacement must be parallel to use this simple calculation. If they're not parallel, then we need to find a component of the force that's parallel to the displacement. So the force, Sean's force times the cosine of theta, that'll give us this component of the force that is parallel to the displacement off to the right. So got to be careful about that. Work is force times displacement, but only if force and displacement are parallel. If they're not parallel, you need to go through a right triangle calculation and find the component of force that is parallel to the displacement. Let's put in some numbers. 135 newtons of force that Sean's applying, cosine of 25 degrees, and 3 meters. I want to find the component of Sean's force to the right, horizontal. That's 122.4 newtons. So force times distance now, 367 joules if I round off, as I usually do when I work problems to 3 significant figures. Intermediate results, I keep more digits. And in fact, I typically don't write things down. I just use what's on the display of my calculator and only round at the answer to the question that's being asked. So this is the work done by Sean. And you should calculate on your own later the force of static friction. But we will see 122.4 newtons is greater than that force if you do the calculation. Okay, what about the work done by friction? The work done by friction. Well, still we have this to consider because the force of friction is in the opposite direction to the displacement. The displacement, the bag is moving off to the right. the force of friction opposes motion. It's off to the left. So there's an angle between those two, and it's 180 degrees, and that will be easy to bring into the calculation. How do we find the force of friction? Well, we have to use the coefficient of friction, and it's the kinetic coefficient, because Sean is able to surpass the force of static friction. So the bag breaks free from static friction and starts moving off to the right. We're going to use kinetic friction, and that coefficient times the normal force, the contact force. So let's continue here. Well, work is equal to the force of kinetic friction times the cosine of 180 degrees and 3 meters displacement. So let's take a look at this force of friction calculation. The force of friction is the coefficient times the normal force. There are two forces involved here in calculating the normal force, the contact force at the ground. We've got gravity pulling the bag of mulch into the ground, that's mg, but Sean is pulling up on the bag a little bit. This upward component of the 135 newtons, that's going to reduce the normal force. So here's our calculation, mg, 45 kilograms, 9.81 meters per second squared, and then upward, and I'm going to take upward as a negative in the calculation here, 135 newtons times the sine of 25 degrees. These two forces oppose to each other, so we have to have a subtraction, and I'm taking mg as the positive. That's a minor point. Okay, so we have the normal force, 45 kilograms, 9.81, that's mg. We've got the component of the upward force Sean is applying, the component of the force Sean is applying in the upward direction. So you should pause and pull out your calculator, see if I've made a mistake here or if we're okay. So I get a normal force of 384.4 newtons. The force of kinetic friction then is the kinetic coefficient 0.25 times the normal force, the contact force. So I have 96.1 newtons of kinetic force. We saw earlier Sean's horizontal component of force is about 122 newtons. So we're, again, just to double check, Sean's force off to the right is greater than the force of friction. This object is going to be accelerating. There's going to be a net force off to the right, and we'll get to that. But first, the work calculation. Cosine of 180 degrees is -1. And then the force of friction, the 3 meters. So the work done by friction is a negative, 288.3 joules. And again, if I round off to 3 digits, minus 288 joules is the work done by the force of kinetic friction. All right, part C asks for the speed of the bag after 3 meters of motion. So we're going to use the kinetic equation here. We're going to assume we're horizontal here for the motion, and we have a constant 135 newtons that Sean is applying, a constant angle of 25 degrees. We can use this kinematic equation because the a sub x will be a constant with what I've described here, a horizontal surface, so we don't have any changing in the direction of the force of gravity and worry about components along that. We have a constant force for Sean and a constant 25 degree angle. So the acceleration will be a constant. The net force in the x direction is going to be a constant. Well, F equals ma. So the acceleration is the net force in the x direction divided by the mass. For the net force, we have the component of Sean's force in the horizontal direction. This was done a few slides earlier. We have the force of kinetic friction, and the net of those is 26.3 newtons. It is a positive. Sean's horizontal pole dominates over the kinetic friction. We're moving off to the right. Our acceleration then, net force divided by mass, 0.5844 meters per second squared for the acceleration. And I misspelled method here. Sorry about that. You can correct that. But 0.5844, hopefully my numbers are right or better than my spelling. Initial velocity is 0. The bag was at rest. We're going 3 meters, and our starting position is 0 meters. Again, pause and do the calculation on your own. Welcome back. So 0 squared here is 0. 2 times 0.5844, and then times the 3 meters. So the square of the final velocity is 3.506 meters squared per second squared. Notice the units are correct here. As I take a square root, I'll end up with meters per second for the velocity. And with 4 digits, 1.873, round off to what we're asking for. Round off to 3 digits, I get 1.87 meters per second. And that's the speed. It's off to the right. So in terms of velocity, 1.87 meters per second to the right. In terms of speed, we just need the magnitude of the velocity, 1.87 meters per second. Now, there's a second way to do this problem. The first method involved the kinematic equation. The second method will take advantage that the change in kinetic energy is equal to the net work done on the object. So we have, for the final kinetic energy, 1/2 mv squared. The bag was at rest at first, so the initial kinetic energy is 0. And then previous slides, we worked out the work done by Sean's horizontal component of force and the work done by the force of friction. So we're going to subtract those two. You should do this on your own calculator. Subtract these two, divide by 45, divide by 0.5, and I came up that v squared is 3.498. I take a square root of both sides. I get 1.870 and round to 3 places, 1.87 meters per second. And if I go back a page, I find that's the same number we had with the other method. So 2 methods for solving this particular problem when we had constant acceleration. The kinetic energy is a little bit more general because we don't need constant acceleration for some other problem. If somebody tells you the work done but tells you the acceleration is variable, you can go ahead with this method and come up with the desired answer. Well, I have a simple website, gpclements.com. I have lists of my YouTube videos for physics and astronomy. Everything's free. You're not allowed to sell it. You don't give me your name or email address, anything. My website does not put cookies on your computer. And the advantage of going here is that these lists of my YouTube videos, there's a direct link to YouTube. And you don't have to do any searching on YouTube. You can just click on the link and the YouTube video will show up. Or you can look at my playlists on YouTube and come up with the video that you're interested in a particular topic, I hope. Well, thanks for listening. Be sure to work more problems and ask your instructor when you have questions.